So in this video, we'll be talking about this theorem, which actually came from the time of the ancient Greeks. And it says that square root of 2 is not rational. So what is square root of 2? Well, if you remember Pythagoras' theorem, which says that a squared plus b squared is equal to c squared, if a and b are 1, then what we have is that this side will be square root of 1 squared plus 1 squared, which is equal to the square root of 2, right? And so that's square root of 2. That's if you have a square and you cut it, square of side length 1, and you cut it across, the length of this side will be square root of 2. Now, what we have to show here for this theorem is that this is not rational. So what do we mean by rational? So you might not have seen rationals before. So a rational number is a number that can be written as m over n, where m and n are both whole numbers, or the integers. Whole numbers would be positive integers, but they can be negative too. And n has to be bigger than 0. If n was 0, then this would just not be defined. So just I'm writing it down. So this would be not defined. So we can't have n equals 0, because then you would have weird numbers like this in the rational numbers. So n has to be bigger than 0, and m can be any number. So you might not be familiar with integers. Some people I know who are doing GCSEs don't really know what integers are, but so I'll write them down. So the numbers, all the negative numbers, the whole number, all the negative, so we have whole numbers like 0, 1, 2, 3, and 4. Okay, these are whole numbers, and so on. But we can, if we allow for negative numbers too, then we get the integers. So that's all it is. It's the whole numbers, but we allow negative numbers too. So this is positives. Okay, and so on. So let's have a look at what sort of numbers are in the rational numbers. So a half is in the rational numbers. Okay, 2/3 is in the rational numbers. In fact, if you put any two numbers, so like 372, and they have to be whole numbers, by the way. It's just that you can't. In fact, it doesn't have to be a whole number. As long as you can make them into whole numbers, maybe by multiplying by 10 or something. For example, 3.7 over 4.2 would be a rational number, because you can multiply both top and bottom by 10 to get whole numbers. Okay. In fact, if you haven't been told about irrational numbers before, you might not. So this would also be irrational numbers. And in fact, if you haven't seen rational numbers before, you might actually believe that every single number is rational, because it's not quite obvious how you would show that a number isn't rational, and that's exactly what we're doing. So this is a theorem. I mean, I wrote the theorem up here. So this is a theorem. In fact, I'll write it down again. Square root of 2 is not rational. How would you show this? Well, so something's not rational. Well, what do we mean by not rational? Well, we mean that it is not true that square root of 2 is in Q, right? That's what we mean by saying it's not rational, that this is not true. It is in it is in the rational numbers is not true. That's what we mean by irrational. So what this looks like something we can use a proof by contradiction on. Similar to the last step. So this is how we're going to start the proof by contradiction. We suppose that it is true. So the theorem says it's not. So what we do is you suppose that the square root of 2 is in the rationals. So, no. Sorry. Suppose.
Okay.
Okay. Suppose it's not true. Sorry about that interruption. Okay, so that means that we can find two numbers, m and n, such that m over n equals square root of 2, okay? But we need we can say something else too, and so this will help us out in the contradiction, that m and n don't share any common factors. That means that m over n is in its simplest form. Okay. So, for example, 6 over 4, you can write it in its simplest form as 3 over 2, right? So, if we say that m and n don't share any common factors, then it's in its simplest form. Okay, so to make this contradiction happen, we have to show that one way we could do it is by showing that m and n do have to have a common factor, and in which case it can't be written as in the simplest form. And as we can see, all fractions can be written in the simplest form, and what we're going to show is if square root of n can be written as n over n, then they can't be written in the simplest form, and so m can't be written as a in fact okay, so that's all there is to. In fact, I should say that again. What we're going to show is that if square root of 2 can be written as m over n, then it can't be written in its simplest form. But all fractions can be written in the simplest form, so that means root 2 can be written as a fraction. So how do we show that m and n have a common factor, even if we say it's in its simplest form, that they still have a common factor? How do we show that? Well, we can do it by first we can bring n up, so we multiply both sides by n, and now we square both sides. We get n squared times 2 is equal to m squared. But that means that m squared is even. Okay, m squared is even. But if m squared is even, that means that m is even. Why? Well, suppose m is odd. That means you can write m as 2 times the letter a plus 1. But when we square that, it's equal to 4a squared plus 4a plus 1, which is equal to 4a squared plus a plus 1. And that's 1 more than a multiple of 2. Well, multiple of 4 in this case, but 4 is multiple of 2. So it's 1 more than multiple of 2. And that means that this entire thing is odd. So if m squared was odd, then m would be odd, right? So that means that m can't be odd, right? And so m is even. Okay. This seems like a bit of backwards, but that's the way you prove it, I think. So we know m is even. So m is even. We're going to just like scribble this out. M is even. That means we can write m as 2 times some number a, okay? And that means that n squared times 2 is equal to 2 times some whole number a, okay? And n squared times 2 is equal to 4 times a squared. That means that n squared is equal to 2 times a squared. We just cancel out the 2's on both sides. Well, that means that n squared is even. And following the same logic from before, we actually see that n is even. Okay. So let's pick some, we can say n is equal to some 2b. So what we find is 2b squared is equal to 2 times a squared. In fact, we can just stop right here, because what we've just shown is that m is equal to 2 times some whole number, which means m is even, and n is equal to 2 times some whole number, n is even. But we said they were written in the simplest form, right? But now we can write it even in a simpler form, right? As a over b. Sorry, not n. It's actually square root of 2. So that gives us a contradiction. We said it was in the simplest form, and now we wrote it in a simpler form. And this means that square root of 2 is not rational, and that means that square root of 2 is irrational. And it's actually quite difficult for people to know what exactly it means for a number to be irrational, and what even is square root of 2. So square root of 2 is equal to 1.414, and so on. And the special thing about writing it out like this is you can tell a number is irrational if the digits never repeat or never terminate. So 3 over 2 is a rational number. It terminates, right? On the other hand, 2 over 3, it doesn't terminate, but the digits repeat. And this is a notation that means that 0.666. But for an irrational number, the digits never repeat. And that's one big difference between rationals and irrationals. So I hope you enjoyed the video. That's about it.